I would say not like really teach machine learning, but help to look at machine learning.
We said teach.
Okay.
Half an hour, I want a PhD in the end.
Okay. It's more like a look at machine learning from a point of view of a JavaScript developer. So, yeah, who of you have ever played with TensorFlow.js? Okay, and with TensorFlow in general? Okay. So I will talk about visual feature engineering with TensorFlow and React. My name is Olga. I'm working as a sales engineer and developer advocate at Accenture, and I would like to start with a short personal story. Before joining my current company, maybe I will make a short 20 seconds break. Yeah. So cool. I will continue with my short personal story. Before joining my current company, I have been working as a front-end and full-stack developer for various companies producing tools for data scientists and implementing different type of machine learning projects. So I was like a JavaScript developer in a world of data scientists. So who of you have had similar experience? No one? Okay. So I was surrounded by a lot of guys with PhD degrees, and it's quite a unique experience. So an obvious question, what I have done there if I'm not a data scientist? And actually we have done a lot of machine learning projects together. And if you will take a look at a typical machine learning project, then machine learning itself, it's only one step in the whole process. Before performing machine learning, you need to aggregate your data from different sources, pre-process your data, and then perform feature engineering. And after machine learning itself, you need to post-process your data to be able to present your results to your users and maybe build nice-looking dashboards, visualizations. So for me, it was always like, I'm doing first step, first part, and last part, but never like central piece, and it was a kind of magic for me. I was always curious to look inside of this magic and learn it, and I always was thinking like, it's the funnest part, and I never had chance to work with this so why? Because at that moment, Python and R and some other languages were commonly used to implement machine learning, and I was more like a JavaScript developer. Then I have seen Google's presentation about TensorFlow.js. And TensorFlow.js is an implementation of popular Python library TensorFlow in JavaScript. And it blew my mind completely. Wow, now I can use tools that I used to work with to implement machine learning in browser and maybe visualize this process and learn it and like understand all this magic. And before going into technical details, I need to tell that there is 3 major ways to use TensorFlow.js. First of all, you can take a pre-trained model, train it, for example, with Python, and use it to predict, to make predictions directly into a browser. There is a bunch of predefined, ready-to-use models, like for image recognition, for speech recognition, for pose detection. You just take it and use it. Or you can take a pre-trained model and retrain it using your own data to adjust it for your particular use case. Or third option, you can build and train model directly into a browser. And this third option works perfectly, fits perfectly into my use case. I want to visualize machine learning process in browser, and yeah, looks perfect. And I was inspired by TensorFlow Playground project. Who of you have heard about this project? Okay, so it's like learning tool, a kind of grandparent for Tensorflow.js library. And this learning tool allows you to define model directly into a browser and specify just like, oops, not working, okay. Specify just some parameters like learning rate, activation function, some other machine learning related parameters, and define your model directly into a browser, define count of layers, neurons per layer, and see how your model will be trained. But because it's like learning tool, they provide only 4 predefined data sets, like here. And you can take one and use it to train your model. And I was like, maybe I can take this approach and apply it for a real world use case. So I decided to implement machine learning using JavaScript and visualize this process, learn it, and then make a step back and apply what I have learned to improve feature engineering. And feature engineering is the thing that I used to work with in the past. So, what technologies I have used? I have used Tensorflow.js, obviously, to build and train my model and make predictions. And I have used D3.js. It's a kind of standard tool to visualize data right now. And I have used React UI tool, library called XReact, that includes several predefined components, UI components that you can use in your application. So for my use case, I have used grid, tab panels, toolbars, and form fields. So I was always like talking about real-world use case. It's time to tell what use case I have used to test my tool. And I have tried to predict results of games played at FIFA World Cups. I have taken FIFA World Cup dataset from Kaggle, and this dataset includes data about all games played starting since 1930 till 2014. And I used this data to train my model, and I used results of games played at the last World Cup in 2018 in Russia to validate my model. So, first of all, I need to define features that will be used in my model, like what parameters might influence the result of football game. And football, I mean soccer game, not like American football game. So what parameters, what features could be used? I spent actually a lot of time trying to find suitable, like nice features, and I ended up with the following list. So previous wins count for team 1 minus previous wins count for team 2 in total, like over the whole time, and in last 12 years means at the last 3 World Cups. Then previous wins count for team 1 against team 2 in total in last 12 years and at the same stage. Then if next parameter is if game was played in team 1 or team 2 home country, I mean country hosting World Cup, and stage is like group game or quarterfinal or semifinal or final. So, and target, what I want to predict. Actually, I want to predict result of this game, and there is only one note. For group stage games, there is 3 options, 3 possible results, like team 1 won, team 2 won, and draw. And for playoff games, obviously, there is only 2 options. Draw is not possible. One team needs to win. And I understand that trying to predict results of football game is a kind of ambitious task for a person who have never built any machine learning model before. So I decided to define a baseline for myself and use model doing random prediction as a baseline. So If we are talking about group stage game, then model doing random prediction would predict correctly 33% of games, like an average. And there were 48 group games at the last World Cup. And for playoff games, obviously, there is like 50% probability that you would predict match result correctly, game result correctly. And it were 16 games at the last World Cup. So model doing random prediction would predict correctly 37.5% of all games. And yeah, now it's a tricky part. I hope I will see my mouse. Hey, where is my mouse? Okay, no, no, it's a video. Okay, now I see my mouse. And I have built a tool that allows you to define a model directly into a browser and define like learning rate, optimize function, and all other parameters related to machine learning model. You can define them in browser, and you can define count of layers for your model and count of neurons or units per layer, and activation function, so you can build model directly into a browser and click run function. I will, for use this example, I will use simple model with only one layer and one unit. And I can click run button, and I will see how my model is trained. So there is all these features, and I see how they correspond to result. So blue line means positive correlation, like positive influence to result, and orange line means negative correlation. And I see there is a number of epoch. It's number changing, and epoch, it's like times to iterate over data during like machine learning process. And I see how weights and biases will be changed over time after every epoch. And here I could also perform feature engineering. Like I can add or remove some feature from my model, and I can apply normalization to a feature. So like normalize this feature according to some specific, I don't know, function. And I use scaling normalization for my data, and once my model is trained, I can validate my model and see that it predicts correctly 36 games out of 64 games. So it's, yeah, I just, for like emergency case, I recorded a video, speeded it up to show you, but it looks like live demo works fine. So my model, my simple model, predicts correctly 58% of all games. And if we will compare to 37.5% of model doing random prediction, it's pretty good result, I would say. So let's take a look at technical details. First of all, Tensorflow.js part. There is the whole pipeline that what we will do with Tensorflow.js. And yeah, let's start with first step, preprocess data. Actually, this step, it's like initial step, and there is nothing to do with Tensorflow.js. We just need to prepare our data to be able to use it with Tensorflow.js. So we split data into two parts, train parts and test part, and we extract like target field, match result in my case, and we apply like feature state, like meta state to my features, like what features should be included, excluded, normalized, and normalization function. Just prepare two data sets. Then there is actual Tensorflow.js part. And central piece of Tensorflow.js are tensors. Tensors, it's a set of values shaped into one or several dimensions. It's like multi-dimensional arrays. And for my use case, I use two tensors, feature tensor and target tensor. And they both like 2D tensors. So I use tf.tensor2d function to create them and send my data and tensor shape as parameters. So 2D tensor or two-dimensional array is similar to table, and count of rows, it's count of games, and count of columns in first tensor, feature tensor, is count of features, and for target tensor, it's one column. Then I need to build my model. As you have seen in graphical interface, I allow to build model dynamically. So define count of layers dynamically. So I just take first layer and tell that it's input layer, and then I chain all additional layers in sequence and add them using layer.apply method. And last layer is like output layer. And I create my model using tf.model function. So model is created. Then I need to compile my model using model.compile method. And now I send all these nice parameters described in machine learning model, like learning rate, optimizer function, metrics, and loss function. And model is compiled. Now I can train it. And to train my model, I just use model.fit method and send both tensors that I have prepared, like feature and target tensors, and some additional parameters, like count of epoch, count of iterations over data, and batch size. It's like size of data that will be used for one iteration. And I also can define several callbacks. And in my case, I will use on epoch end callback. So I will be notified at the end of every epoch, like end of every iteration over my data. And I will use this callback to update my visualization. My visualization built with D3.js. So, and once model is trained, once training process is finished, I can predict results. And to predict result of one single game, I just create tensor using value for these games, like all features of this game. And I send, of course, a shape of tensor, and I use model.predict method, send this tensor as parameter, and read results. So this read.js part. How I actually render this visualization. I will not go into details of this read.js visualization, since I will just look at this from like bigger scale. And I just render panel component and with a header, and define epoch number as title for this header. And then I create SVG inside of my panel. And every time when epoch ends, a refresh function will be called, and layers describe current state of my model. So this layers, it's an array of like all weights, biases that describe current state of a model. And based on this current state of a model, I just generate graph data and render, update nodes and edges for my graph. And actually, this panel component that I have used in render function is an XReact component. And I use several XReact components in my project. I use tab panel to switch between like train and test data sets. I use toolbar, I use combo boxes, number fields, buttons, and I use grids to visualize my test and training data sets. So it's quite nice grid. It allows you to filter data. There is sorting, grouping, pre-built sorting, grouping capabilities. And I could also extend the menu for column and add this normalization scenes. And I could hide and show some columns. So how it looks like. I will show only grid describing training data. So I send store that includes all data from my tensors as prop. I define all features as columns, and I tell that I want to use grid filters, like built-in grid filters plugin. I define some styling parameters, and I can also be notified once some column will be hidden or shown. And I use this handler function to rerun my model. So let's take a look at the whole application at a bigger scale from React point of view. And I have just top level component panel, and layout prop describes how child components will be positioned inside of parent component. And I send initial state of my model as config prop. And once this model setup will be changed and run button will be clicked, I will rerun my model inside of on config change function. And then I have this visualization component, and I send layers and epoch as props. And layers describe current state of my model, and epoch describe number of iteration over my data. And these values will be always changed at the end of every epoch, and my visualization component will re-render this React.js visualization. And then I have tab panel with two grids, and one grid, it's like a grid describing training data, and I send all features as fields, and current feature state, like what it's included and excluded, normalized as meta, and then my training data set as tensor, and once like some features will be normalized or excluded, then on fields change method will be called, and it will rerun my model. So let's try to do a fun part and try to improve my model. So I will not do it live. I just recorded these videos and speeded up them a bit, but you have seen that the whole training process takes like 2 minutes, maybe 3. So of course, my original idea was to add more layers to my model. Here it's 3 layers, and there is 7 units in first layers and 3 units in second layer and 1 unit at the last layer. And I thought, like, yeah, more is better, and this model will do better prediction. But actually not. It worked even a bit worse than the original simple model. And I came to conclusion that it's the only way to improve my model is to improve feature engineering. And if we will take a look at the model visualization at the end of training process, we will see most valuable features. And these most valuable features have thick lines. Like, thick line means higher influence to result. So most valuable features are previous wins count for team A, team 1 minus previous wins count for team 2 in last 12 years, like at the last 3 World Cups. Then previous wins count for team 1 against team 2 in total. I believe it's because teams play not so often against each other. And then home country and stage. So I have tried to run model that includes only these 4 features. It's much simpler model, and training process will be much faster. And it works almost as good as model including all features. Almost the same rate. And then, of course, I tried to improve this model with more layers and units. Didn't work as before. A bit worse the result. Then I said, wow, maybe I can use the simplest model with only 1 feature. And I have used previous wins count for team 1 minus previous wins count for team 2 in last 12 years. And actually, this model worked not so bad, and it predicted correctly 50% of all games.
So I decided that optimal model would be model including 4 features. There's 4 most valuable features. It's quite simple. It will be trained and quite fast, and it will predict results quite good. And based on this visualization, final state of my model, I can tell interesting insights. First 2 are kind of obvious. Teams that won more games in the last 12 years perform better, obviously. Teams playing in home country perform better. Yeah, kind of obvious. Third one was not so obvious, at least for me. Weaker teams perform better on a higher stage. And last one was a kind of surprise. Teams that lost more games against this opponent in the past perform better. So it's this line, this orange line. So I need to mention that for my tool, I used only dense layer type for my models. It's suitable for many use cases, but for maybe more complicated models, it will not work. I'm considering an option to add this other layers to my tool, but the thing is that it's much more complicated process for visualizing these layers. And in my visualization, in my model visualization component. So please feel free to take this project and apply maybe for your own data and try to build your first model visually using graphical interface. Just define a model directly into a browser and perform all feature engineering. So everything that you need to do with this project is just to change underlying data set. There is a link to my source code of my project and live demo. And there is also a link to original data sets that I have used for my project at Kaggle. Yeah, and if you will play around with my model and will find a model doing better prediction, please let me know. I'm really curious. I didn't find it. So I will publish slides and all links at my Twitter. Thank you.